morning, everyone. This is Dr. GVR Seshagiri Rao, Associate Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today, in this session, I would like to discuss about endurance limit and fatigue failure. The endurance limit and fatigue failure criteria are very important while designing a machine component. So, what are the factors affecting the fatigue failure, and how to take the endurance limit and how to calculate this fatigue strength, we will discuss in this session. So, endurance limit, before going to the endurance limit, so first we should know what is fatigue. Fatigue means whenever the component or element subjected to repeated loads or repeated stresses, that means cyclic loads, after some few cycles the component fails. So due to the minimum stress applied to below, so that means the stress applied below the yield stress. Such type of failure of a material is known as fatigue failure. So generally these type of failures occurs in the crankshafts and the piston rods, clear, and connecting rods also. So this the fatigue failure, so experimentally found whenever the subjected to repeated stresses. Clear. The fatigue strength or the fatigue life of a component you can calculate by using rotating the fatigue beam tester. So the failure is caused by means of a progressive crack formation, clear, which are usually fine and of a microscopic size. First, initially, so some cracks will occur in the component. So after that, after some few cycles, the failure may occur even without any indication, prior indication. So directly component fail. So without prior indication means in ductile materials, first it will indicate through deformation. So that is yield point. So lower yield point and upper yield point already we have studied in a stress strain curve. The fatigue of material is affected by the size of the component. So that is relative magnitude of static and the fluctuating loads, and the number of load reversals. So here for testing purpose, a mirror polish, the standard mirror polished specimen is used. So as shown in figure, I will show you the figure. It is rotated in a fatigue testing machine. Clear? When while the specimen is loaded in a bending. Clear? This is the standard specimen. This standard specimen tested in a fatigue beam tester. This is the polished one. As the specimen rotates, the bending stress at the upper fibers varies from maximum compressive to maximum tensile stress, while the bending stress at the lower fibers varies from maximum tensile to maximum compressive. So whenever this component specimen rotated in a fatigue beam tester, so what will happen? So always the upper fibers are subjected to tensile stress and the lower one is the compressive stress. At axis there is no stress. So that's why it varies from compressive to tensile and tensile to compressives. So in other words, the specimen is subjected to completely reversed stress cycle. So what is this reversed stress cycle? I will show you. So as the specimen rotates, so already we have discussed, there are top fibers subjected to tensile and the lower one is compressive. So that's why, so one time the maximum compressive to maximum tensile and maximum tensile to maximum compressive. Here, the represented by a time stress diagram. Here, stress plotted on y-axis and the time is plotted on x-axis. See, this curve follows the sinusoidal curve. Clear. So in this, it varies from maximum and minimum to maximum and maximum to minimum. So this is stress amplitude. So we can calculate the amplitude stress is sigma max minus sigma minimum by 2. Here there is no mean stress. Okay, it is fully reversed. So endurance or fatigue linked means it is the maximum value of the completely reversed bending stress. So that is which a polished standard specimen can withstand without failure. So already we have tested one specimen. So had to be that specimen had to be had to which the withstand the failure. So that the limit is called as endurance limit. That is higher higher limit value, endurance limit or fatigue limit in case of fatigue loading. In the case of normal loading, the tensile load or a compressive load, generally we will take ultimate stress. Ultimate stress is the maximum point. Clear? So here, here you can take the infinite number of cycles is usually 10 to the power of 7 cycles. Clear? So beyond this 10 to the power 7 cycles, the component cannot withstand the failure. Clear? So it may be noted that the term endurance limit is used for reversed bending only, while for the other types of loading. Clear? The term endurance strength may be used when referring the fatigue strength of the material. So also it can be defined as the safe maximum stress, clear, which can be applied to the machine part working under actual conditions. That is we can say the safe limit. Clear? So we have seen that when a machine member is subjected to a completely reversed stress, the maximum stress in tension is equal to the maximum stress in compression. Clear? That's why the maximum and the minimum stresses are equal here. That's why the mean stress is 0. Clear? In actual practice, the many machine members undergo different range of stress than the completely reversed stress. Here, one more stress is there, that is fluctuating stress. In this case, here also stress varies from minimum to maximum and maximum to minimum. But here, the maximum stress value and the minimum stress value are not equal. So that's why there is the mean stress. So we can calculate mean stress is equal to sigma max plus sigma minimum by 2. So this curve also follows sinusoidal. The major effects affecting the major factors affecting the endurance limit. The strength of large members is lower than that of small specimen. Already we know the strength of large members is lower than that of the small. Why? Because the larger member will have the larger distribution of the weak points than the smaller one. So already we have studied in stress concentration. So in that case, the flow lines or test distribution lines are very weak. Clear? In larger components. So always that's why prefer smaller component within the limits only. Clear? And then the larger members have larger surface areas. So this one also one type of cause the imperfections occurred in the component. That's why the size effect affecting the endurance limit. Clear? So while calculating the endurance limit, you have to multiply the endurance limit of the actual component, design stress, designed component, multiply with this size factor. We can represent with sigma s, or you can write sigma size. This second one is surface roughness. So the conditions of the surface roughness and surface oxidation or corrosion are very important. So here poor surface roughness also caused to fatigue failure. Clear? The experiments have shown that different surface finishes of the same material will show different fatigue strength. So already number of experiments conducted for determining the fatigue strength. Clear? So with the methods which improve the surface finish and those which introduce compressive stresses on the surface will improve the fatigue strength. Clear? And this the smoothly polished specimens So already I have shown in the previous slides. The polished specimens have higher fatigue strength. Clear? So that's why we are tested that the type of polished specimens for fatigue strength calculations. The surface treatments, fatigue cracks initiate at a free surface treatments can be significant. Clear? And plating, thermal or mechanical means to introduce residual stresses. Some residual stresses also cause it to the fatigue failure. The third one is effect of temperature. So that's why the working conditions also very important while designing a machine component. Clear? Have to check operating conditions while selecting the factor of safety. Also, we have discussed in factor of safety topic. Clear? The atmosphere conditions also to take considerations for designing. Fatigue tests on metals carried out at below room temperature shows that fatigue strength increases with decreasing temperature. Clear. So the room temperature shows that fatigue strength increases with decreasing the temperature. If the temperature is decreasing, the fatigue strength will increase. If the temperature is increased, the fatigue strength will decrease. Next, fourth one is the effect of metallurgical variables. So the fatigue strength always generally increases with the increase in ultimate tensile strength. Clear? So the fatigue strength of the quenched and tempered steels and have better fatigue strength. So that's why the material always should be heat treated. Clear? Due to this heat treatment process, like tempering process and martensitic structure will vary. And normalizing. These all are heat treatment process. So you can obtain the better grain size. So that is fine grain size. So better fatigue strength than coarser grain size. Clear. So whenever the grain size is fine grain size is obtained in the component, then the component definitely having good fatigue strength. Clear. The non-metallic inclusions either at the surface or subsurface reduces the fatigue strength. So this one also one cause to the failure. Thank you. So these are the references we have taken.
Like, share and subscribe. Hit the bell icon for more updates.